Did you do some exercises?
I tried to.
Okay, it's very good. No, which one?
The first two problems.
No, about what? I don't remember.
I think about proving the homomorphism.
About exactness of homomorphisms?
Yes.
Or, no, please, tell us. Okay.
No,
We start our seminar, and our seminar is about your exercises. Yeah?
No, I tried, but I didn't succeed.
You did not get answer?
Yeah.
Ah, no.
What is the first problem?
No, it's about exactness of Hom. It's a very important exercise about exactness of Hom and exactness of tensor product, yes? Exactness in some places. No, do you have some exercises which you done?
No, for now.
Okay. Did you have some exercises which you?
Yes, I did something. For example.
For example.
This problem.
Exactness of Hom and tensor product in some places.
Yes, but I did in different setting. I did for functor of extension scalars like this.
Ah, okay. No, okay. If we have short access sequence of, for example, left modules, and we have some left module, then we have Hom over R from M A to N, Hom A to K, and we have obvious injection in this place. Yes, it's obvious. Yes. Yes, maybe no. Yes, we have F G. This is F star G star. It's by definition for you. It's hello. It's post-composition. Yes, it's if we have some homomorphisms from here, then it goes to phi star of phi. It's phi post-composition. Yes, and then if we have some psi from this, then it goes to G star psi is post-composition with. Okay, it's by definition. Huh? And I claim that this sequence is exact. At this place, no, and these two places, yes. At this place, that means that this homomorphism is injective, but it's more or less obvious, yes? If F is injective itself, then this map is also injective, okay?
I want to clarify this notation. What does this mean? Homomorphism of?
Homomorphisms is phi from A to M, which respects addition and multiplication by elements of your scalar ring. And it's just abelian groups.
The ring, right?
Yes, it's modules, it's left are modules over some ring. M, N, K, A, left are modules. Over some, not necessarily commutative ring, and then if R is not commutative, then this is just abelian groups. If it's commutative ring, then it's also R module, but it's not important for exactness, because exactness is for abelian groups and for R modules it's the same thing. Что?
So M and K are modules, right?
Yes, and A also. No, for example, left or right, of the same direction.
Okay.
Modules, yes. We have this sequence of homomorphisms of abelian groups in general. And I claim that this sequence is exact in this place and in this place. Exactness in this place means that F star is injective, if F is injective. No, it's obvious, okay? Maybe you did some these exercises, no?
Well, I tried, but...
Exactness in this place is not.
Yes.
No, also if we know that we know that ker F is image of, image of F is kernel of G, it's exactness of this sequence. And so, this means that composition GF is 0, and then, of course, we have composition stars is 0, because it's composition GF of phi, for example, okay? And so we have, of course, that, this means that it's equivalent to say that kernel of G star contains image of F star. So this is also obvious, okay? No, it's because G star F star of phi, it's GF phi, and GF is 0, okay? So this is 0, and this is equivalent to say that image of this in the kernel. of the following arrow. So not obvious part, it's why we have opposite inclusion. Why we have image, kernel of G star in image of F star. So what does it mean? If we have some, no, let's formulate this. If we have some psi from A to N, and we know that composition G psi is 0, then we must, как это сказать, must exist, как сказать, должен существовать, как это будет. There must be some phi from A to M such that psi is composition F phi. It's what we know. This means that kernel contained in contained in image.
Can you see the F star and G star functors, right?
No, F star and G star is just induced homomorphisms. It's because Hom is functor. Hom from something fixed to something, it's functor on second variable. Yeah. And this induced, and this is a functor on these maps. Yeah. This covariant functor. Okay. Yes. Yeah. Functor Hom from A to something.
And this is how you wrote geo phi, geo xi equal to 0.
What?
How you wrote geo xi equal to 0.
It means that psi is in kernel. Yes. Kernel of G star. I pick some element from kernel, and I want to prove that this element from kernel in fact in image of F, because this means that psi is F star of some phi. It's what I want to prove. I want to prove that this inclusion, if I have element from kernel, then in fact it's in image. It's what I want to prove. Because this inclusion is obvious, I want to prove exactness means that I have equality. It's exactness in this place. It's the definition of exactness. The kernel image of this map exactly the kernel of the following map. I know this inclusion. It's obvious, and I know the opposite inclusion. It's what I want to. It's what remains to prove.
We need to construct.
Something like this.
So we need to prove this kernel of G star lies in image of F star.
What? It's. Yes. It's what we need to prove. It's the same. It's reformulation. It's unwinning definition of this thing.
Is it the same?
Of course, because the first class is similar. So it's in the table.
Okay.
They're similar. No, to understand the previous lecture, and the next is the following lecture.
Yes.
With new, not understandable things. To be understood on the next thing.
Okay, I forgot the notation. Okay, for every psi.
Not for every. You consider
I
one.
forgot the notation. Zero. Okay, this is psi from kernel.
Yes. And you need to find some phi. No, it's psi.
Wherever is this psi, such that this is zero, exists also.
It's the claim.
So we need to construct it just by hands.
Yes.
Yes, I want to look at this equality. So if it existed, then it must satisfy this property. Then I want to
No, it's not important. In fact, the surjectivity of G we will not use. It's not important.
Why G composes psi 0?
Because we consider element from kernel of G star. Psi is from kernel, and we need to prove that kernel G star is in the image. And we consider some element from kernel, but element from kernel means that G star of psi is 0 and G star of psi is composition G.
It's just initial. We took psi from kernel of G star.
Yes.
Initial.
Yes. We consider some element, and we need to prove that this element, in fact, is from image of F. In fact, it has the form F composition with some phi.
Yeah.
It's F star of some phi.
I see. So we are proving the inclusion that kernel of G star is an image of F star.
Yes. No, it was here, but your colleague cleared this part of the board.
And do we need to prove this when A is on the right?
No. No, yes, we of course we need this, but it's independent statements.
Okay, can I prove when the A is on the right first, because I think it's easier to see. Because
I think the left is easier, but okay. No, if you if you want, but no, then okay, reformulate all our statement. Okay.
Yes. For me, it's much clearer because there I have subjection, and then I can prove it.
Okay. Oh, back. Okay.
You will see.
Well, back of element you mean pre-image? Okay.
Yes, pre-image.
Okay.
Of course, pre-image.
Okay, now your colleague decided to prove another statement about exactness of Hom to something fixed. Also exactness from the left in this part and in this part.
Here it is, it means that the match from him to
Yes, to A, yes. No, in fact, this starts. Yes, it's no. You're right. But what starts now? Yes, it's yes. You're right, and then stars upper stars because they are contravariant.
Of course.
It's a precomposition with J and with F. Understand the definition of this? Again, injectivity on the left is more or less obvious because of the surjectivity of G. Okay?
Here it must be the same argument about.
And by the same argument, composition is 0. So again, we need to prove that kernel of F, in fact, is in the image of G star. No.
Yes.
No.
Yeah, of course. I am sleeping.
А вот надо на пары по физике перед этим ходить, чтобы просыпаться на них.
Я 5 минут назад встал.
А, вы тут живете в общаге?
Нет, близко.
Yes, it's what we need to prove. It's not obvious one. Yes. Injectivity of G star follows from the surjectivity of G, in fact, also in obvious way. This is not obvious part, no, relatively. If we have some, element, some phi from upside from N to A, yes. From N to A.
I understand what I'm doing.
Yes, we consider precomposition psi F N to A. Then it must be some element phi, yes. Psi. No, maybe write the question mark because it's our claim. It's not.
Yes, yes,
we don't know
course.
this existence. Maybe yes.
Now this is what was funny. I first thought about this diagram. So we need to, just by definition, we want phi of g of n equals to psi of m. Yes, but then
And this definition is correct, yes, because of the. Yes.
now I want to see that. So I want to define phi on some element k.
Yeah, no, you can say that this is definition because elements of for j of n, it's all elements of k, and if you, it may be the definition of phi, and this definition is correct. Yes, you need to check that. No, the definition does not depend on preimage of n. Yes, you're right. Something like this. No, this formula already define your values of phi on all elements of k. Maybe it's not correct, maybe it's not unique, yes, but
yes, I understand. Yes, because it's injection, but that's what I said. I just wanted to say it in other words that for every k exists such n such that this holds. But then
and we define it psi of n. Yes.
Yes. And then in definition, this will be psi of n. Yes.
And why it's correct?
Yes, we must check this.
Or
Consider if we have another preimage. So since it is equality, okay, we have 0. Then this means that lies in the kernel. I need to use this G. This is the image.
And then exactness of the original sequence. Yes.
This means that exists L. So
Yes, the difference is the image of m, and then psi of the difference is 0. Yes. Psi of the difference 0, so values of psi of n and psi of n prime is the same. Okay. Yes. It's 0.
And it's correct.
Yes.
So this is correctly defined, and
Yes.
obviously this is
No, Abelian group homomorphism. Yes.
yes, this is Abelian group homomorphism, but this is obvious because for preimages something are k. If for k we have some preimage n, then we can take
Preimage of R of the same form. Yes, of the form R of something. Yes. And for additionals. Yes. Okay.
this is what.
Yeah, thank you. But I think that this part is more obvious because, okay, if you have this composition is 0, this means that the values of this psi is in the kernel of G. And this is the same thing as the image. And this means that psi of A is some f of m, and this m is unique because this is an injection, and we just say that phi of A is m. And so it's all.
Once again,
this composition is 0. It means that values of psi, no, psi takes values in kernel of G.
Yes.
And kernel of G is the image of F.
Yes.
So for any A, there exists M such as this form. And this M is unique because F is injective. And then I define in this way. No, it's in the image. And they just take values in image. And this image is injective. So
Hence it must take.
unique M, because of the injectivity of M, of F. And so I can define, no, it just goes through the kernel is just M. So it goes through M. Psi goes through M. And this is unique phi.
Yeah, okay,
I think this is more obvious than this part. It is also not hard, but I think it's just obvious, more obvious, okay? Okay? No, and we have also exactness of tensor product. Do you want to consider tensor products? No, maybe it's a little bit less obvious, maybe it's a little bit less familiar than Hom's, if I have the same. No, in fact. Then I claim that if it's exact sequence of left module, and I have, for example, right module, I can consider tensor products. And I claim that this sequence is also exact sequence of abelian groups. What's tensor product? Tensor product, no, for example, it's this is something generated by tensor products, formal things. No, modular relations, yes? And no, definition of the induced homomorphism also obvious. Yes, it's obvious. It's kind of, no, it goes to something like this. More generally, if you have two morphisms of left modules and of right modules, then, then of course you have tensor product of them, Fg, and you have something like this, F tensor G. And this is F tensor ID, and this is G tensor ID. No, and of this form, yes? Goes to F, M, G, L. It's correct if F is homomorphism of right R modules and G is the homomorphism of left R modules, then it's correct homomorphism of abelian groups. It's respects all relations. Because if we have some R here, we can consider it here, and then consider here, and then consider here, no, something like this. Okay? This is F tensor ID and G tensor ID. Okay. Again, surjectivity of, no, again, it's obvious that composition is 0, it follows that composition is 0, and surjectivity is also obvious because, no, by definition, the tensor product is generated by elements of this form, and any element k is image of some n. It's so this is image of na. So no, we obtain all generators of this abelian group, and so image is all group. Okay.
So is this L or N? N goes to K.
Are you also participant of our course?
Sorry? Yes.
Okay. Hello. What?
Should be L or N?
Where?
The capital L.
Go into K.
Here?
Right side. Yeah.
It's L. No, it's L. It's more general situation. If you have homomorphism of right modules and homomorphism of left modules, then you have induced, no, tensor product of this homomorphism is homomorphism of abelian groups, n, k. No, from m to n, from L to k, then you can consider tensor product of these homomorphisms and obtain the homomorphism of abelian groups. No, defined by this rule. Tensor products generated by elements of such form, modular sum relations. And I define this homomorphism on generators, and you can check that no, this definition respects all relations, so it's defined homomorphisms from tensor product. Tensor product generated and some relations, and these homomorphisms respect relations. Okay. And I say this because no, this F star and G star is just F tensor ID. I have identity homomorphism on A I do nothing, and I have homomorphism F on M, and this is not the same thing. Okay. I can define it on generators, but no, I say that I have some sums of some elements. It's any element of tensor product have this form. It's some sum of these elements, of such elements. Okay.
So what we are trying to prove here?
I say that the first. Again, I know that the composition is 0, so composition is also 0. It's obvious. Okay. Again, if G is surjective, then this map is also surjective, because if I have some elements of this form, K has form G of something, and then this is G star of something. So all these elements are in the image, but these elements generate this group, so this group is also in image, so this G star is surjective, okay? No, any element of this tensor product is some of these forms, and this is G star of Ni Ai for such Ni that Gni is Ki.
I think we are trying to prove the same thing as before. But
Yes, I prove exactness of this sequence, of course, yes. And I say that surjectivity, exactness in this place, surjectivity of this map, is more or less obvious consequence of the surjectivity of G, okay? Because if I can obtain any element of K as an image of G, then of course I can obtain element K tensor A as image of N tensor A for some N. Because I do nothing on A and I just apply G on the first tensor factor, okay? It's obvious. It's obvious or not? No, okay, and now, again, not trivial part, it's why image is exactly the kernel. So why kernel of G tensor ID is in image of F tensor ID. It's F star and G star. Okay. I have, now consider N tensor A. I have image of F tensor ID, it's some abelian subgroup. And this abelian subgroup, no, I know this fact. So if I consider I have this homomorphism, and image of this subgroup is in the kernel. So what I want to say is that I can, no, this homomorphism go through the quotient. I want to say that I can consider quotient by image. And I also have homomorphism of abelian groups. Okay, it's because its image goes to 0 by this homomorphism. Okay, I will define it by the same later. No, it's induced homomorphism on the quotients. Okay, on the quotient. It's because I know this part. This part I know. Image in the kernel, so I can. No, if I quotient by kernel, I obtain the image. I obtain the same thing. It will be isomorphism. And now I consider quotient by the image. Maybe it's not isomorphism, and I claim that exactness is the same thing that this homomorphism is isomorphism. No, the equality is equivalent to say that this is isomorphism. It's isomorphism. Because it's will by isomorphism kernel, because it's theorem about homomorphism. Quotient by the kernel is isomorphic to image, and I know that image is the same, is a whole group. And now I want to, no, I have this homomorphism because of this inclusion. And equality, equivalent to say that this как это сказать, this concrete homomorphism is isomorphism, okay?
In real sense, this is equal, right? Kernel G star.
Equivalent, yes. No, maybe I can define this homomorphism if and only if I have this inclusion. I know this, and this inclusion is equality if and only if this homomorphism is isomorphism. No, because if you want, because in general this homomorphism is surjective, and its kernel, its quotient, kernel GID modulo image FID, and its isomorphism if and only if its kernel is 0. Okay.
We want to show this inclusion, but it looks like it's already implying this inclusion is proved. But we want to prove it.
Yeah, this inclusion is proved. We need to check that this inclusion is equality. If we have this inclusion, we already proved this. And if we have surjective, then we obtain surjective homomorphism from this to this with this kernel. And we want to prove now that this kernel is 0. It's equivalent to say that this subgroups coincide. And then it's equivalent to say that this homomorphism is isomorphism. Okay. No, I just want to check that these homomorphisms are isomorphism, okay? No, now I can define the inverse to this homomorphism. Так.
But why are you extracting out image of star ID?
What?
Why are you extracting out image of a star ID tensor product?
I don't understand what you.
Why take the question of n star n cross a?
No, because this image is some subgroup. It's image of this of MA in this subgroup. Yes. It's contained in kernel, so it goes to 0. So I can define this homomorphism on the quotient. Okay. Because if I have some homomorphisms of abelian groups, and I have some subgroup which goes to 0, I can define homomorphism from the quotient. Okay. No, because on the quotient class you can define by this thing, and this is correct because for any other element from the class, this is the same thing because f of c was 0. Okay. Okay. And if my original homomorphism was surjective, this homomorphism is also surjective, and this is my case. I have surjective homomorphism. I already know this is surjective. I have this inclusion. So this subgroup into the kernel of this map, so I can define this quotient. This quotient map is also surjective, and I have some kernel of this form. Kernel of this thing is exactly kernel A quotient C. No, C is in the kernel because f of C is 0 is equivalent to say that C is inside the kernel. Yes, into the kernel, and the quotient is exactly the kernel of the quotient map. And so I want to check that this quotient is 0, that these two subgroups coincide. And it's equivalent to say that kernel is 0, it's equivalent to say that this homomorphism is an isomorphism. Okay? Okay. Okay, now I want to define the inverse homomorphisms. Now maybe.
Can't we just, we have adjunction of functors between Hom and tensor product. Can we just, use this adjunction just using Hom and, use previous programs?
No, in fact, maybe you can. Maybe you can, and if you can, please tell us in the next time, okay? Or maybe now, if you can think about it. Yeah, maybe. In fact, I do not remember. Maybe if it's obvious, but I just don't remember now. Maybe it's not enough. I don't remember. No, this is kind of direct proof. Yes, I choose to give you a direct proof. From Adjunction, yes.
Homomorphisms to R, we need to consider homomorphisms to R. And then these theorems.
Okay, yes. In fact, you're right. In fact, okay. Let's see. To use Adjunction, you have some Hom to something or to something because in Adjunction you have tensor product on the left to something. Yes. But to what you consider needs to Hom? To R? No, but Hom to R is not exact. No, it's not equivalent to say that this sequence is exact if and only if Hom to R is exact. It's not right. But in fact, there exists. For example, something like injective abelian groups. You can consider some injective something like Q modulo Z or something like this. Then this exact sequence of abelian group is exact if and only if Hom to Q modulo Z is injective. Yes, and is exact. And if you consider something, you consider adjunction. No, okay, yes, maybe, okay, let's do it. This thing is exact if and only if I consider some Hom to some injective abelian group. For example, no, sorry. No, what? I wanted to discuss this something later, but okay, maybe we will discuss now. It's true that if you have some just two maps in abelian groups, for example, then this exact, if and only if, form two, no, if it's modules, then modules. Oh, sorry, as abelian groups. To Q modulo Z again, in opposite direction. Abelian groups. It's called sometimes opposite or dual modules, or dual abelian groups in this case. But in fact, no, if it's R module, left R module, then it's right R module. So it's dual right modules. And it's true. And if you know this thing, maybe you can do adjunction argument. But it's not obvious because we know injectivity of this group. This means that from this exactness follows this exactness. But the opposite direction is not, we do not know so far, okay? No, it's not obvious that from the exactness of this group, no, it's not true that for injective abelian group, from exactness of this part follows exactness of the original sequence. It's not true, for example, for Q. It's not true. So we don't know this. And so if you, by some argument, obtain exactness of this sequence, it does not give you exactness of the original sequence of the tensor products, okay? I consider, our original product is this product. If you consider Hom to QZ and then use Adjunction, you obtain something exact, but maybe it's not sufficient to obtain exactness of the original product of tensor products, okay? But it's true, in fact, and in fact, you can do this, but we don't have enough knowledge about modules and abelian groups to do this. I think. But I maybe if I will have time, I will discuss this on the lecture today, maybe, or maybe on the next lecture about flat modules. Now, direct proof. I need to define the inverse homomorphisms. No, yes, if I have some tensor of this form, I define homomorphism is just in an obvious way. Yes, I consider some pre-image and consider quotient of this form, class of this form. It's correct because if I have another pre-image, then they differ by element in the kernel of G. But kernel of G, we know that the original sequence is exact, so the kernel of G is the image of F, so the difference is from the image. And so this quotient modulo image is the same class. We know this. So this homomorphism is correct, and you can easily check that this in fact the inverse homomorphisms. That this composition and this composition are identities. That's all. It's more or less also как-то, не знаю, как это по-русски. В общем, выглядит как обман. It looks like some blah blah blah. But it's all correct. It's correct proof, in fact. No, you can check that these compositions are identities, in fact.
If kernel G equal to image F, so it's compulsory that the composition should also be equal.
What?
So if kernel G is equal to image F, so is it compulsory that the composition should also be equal?
No, to identities, because I claim that this is the inverse homomorphism to this isomorphism. I want to check that this is isomorphism, and I claim that I construct inverse isomorphism. So you need to check that these identities are, this composition are identities on this group and then on this group. No, this is kind of F, and I claim that G tensor ID F is identity on this group, and this composition is identity on this quotient. So, this means that this is inverse isomorphism. Okay, I just construct inverse homomorphism, more or less indirect way. No, we use subjectivity here, and we use that image is exactly the coordinate in the original sequence to check that this homomorphism is correct. Окей? Ну, кстати, вот если вот именно про тензорное произведение, возможно, если вы будете искать в книжке по геометрической алгебре, там, возможно, какой-нибудь будет adjunction, но используя уже какое-то дополнительное знание про дополнительные активные модули. Но для хомов, вот, ну, для хомов вы видели, что совсем все очевидно, хотя ну, тут вот можно и тоже прямо. Так, окей. About extension and restriction and coextension of scalars. About projectivity and injectivity and so on. It's the first time. Oh, maybe no. Maybe, okay, yeah, no, about projectivity and injectivity of scalars. Yes, it's the first time. It's the motivation why we need some. No, yes, and in fact, of course, we have no exactness on the final part of the sequences. Yes, for example, Hom. Okay, Hom A N, Hom A K. This part may be, this map may be not surjective, and this is the place where homological algebra arises, in fact. But okay, it's kind of the beginning of homological algebra, not homological, just algebra. Okay, and it was the first main result from this part of algebra. Now the second part is about projective and injective modules. Did you remember and understand the definition of projective and injective modules? Okay, we proved that. Yes? No? Why? No, okay. I recall. No, projective module is just module such that if we have surjection, exact sequence of this form, and I have map to n, then there exists map to m. Okay. It's the same thing to say that if I have, no, I can consider kernel here. So any surjection can be uniquely included to the short exact sequence. And then this just means that, no, if I consider Hom from P to this short exact sequence, then we have already known that we have short exact sequence of this form. It's for all modules true. But this property means that this map is in fact surjective. Because for any homomorphism from P to N, there exists some lifting. And this lifting is exactly the preimage of this map. If it's F, it's F prime. Then to say that F star is surjective is the same thing to say that this map has this lift. Okay? Okay? And so this is this module called projective, if and only if Hom from it to any short exact sequence gives you short exact sequence. Also exact on the right. Okay? And for example, free modules are projective. Did you check it or did you understand this? Do you understand that any free module is projective? No, we discussed this because for free module we can consider preimages of the for basis. And then this defines the module map from free module itself. So free modules are projective. If it's free module with some basis, we have some images of basis. These images we can choose some any preimages. Then we obtain some map from basis to M. But any function on basis to M, uniquely extend to the R module map from free modules. Okay, from free module to M. And so free module is projective. It's example of projectives. And we know that we prove that any module have resolution of projective modules. Resolution means that it's exact sequence of modules and all these modules projective. For example, we can consider them are free, in fact. Okay. And also we proved for injective. Injective is the dual situation. Injective means that if we have inclusion of modules, and if we have map from the smallest, from smaller one to I, then there exists extension from bigger one. This means that I can include my injection in the unique way to the short exact sequence. And this means that in the corresponding short exact sequence. This is, of course, always exact. We already proved this just right now. But injectivity means that this sequence is also exact on the right. But subjectivity here, again, means that if I have some map from K to I, then there exists some pre-image. Then there exists some lifting. And this is the same thing, OK? So injective modules, it's such modules that sends, such that Hom to them send short exact sequences to short exact sequences, OK? It's equivalent to say, OK? No, we know that for any module I here, this and this place are exact, and the exactness in this place is equivalent to say that this I is injective. If it's true for any short exact sequence KMN, for any. And in fact, we proved, it was, I think, maybe the most non-trivial part of the first lecture. We proved that any module can be embedded to injective one. Mm-hmm. And
also, this is also true if you reverse it, right? I N,
what?
I N, I K. If you also
no, it's another. What?
Yeah, instead of Ni, if we just map it from I to N, this holds.
I consider map to I.
No, homomorphism I, comma N.
Where?
If we take.
If we take.
Yes. So this.
If we take, then we no. If it's not projective, I just obtain exact sequence without exactness on the right. I have this thing. This sequence is exact for any modules M and N and P, and exactness on the right here is equivalent to say that the left module is projective, and the exactness here is equivalent to say that the right module is injective. If it's true for any M and K. Mm-hmm. For any M and K. Yes, and we proved that any module can be embedded to injective one. For any module, we can consider injection to some injective modules. Injective module. And from this, we obtain injective resolution also. It's exact sequence such that all these modules are injective. Yes. But here we use, I think, coextension of scalars. So, so I think we need to check this now, in fact. But if you remember the construction, in some step, we used, in fact, some exactness of these sequences already. But also we used something like, if we have, if we consider Hom from R, of Abelian groups, from your ring R to, for example, Q modulo Z, then this is R module, right R module. If R is left, we consider left R module structure, then this is right R module, and as right R module, this R module is injective. But this is right R injective. We have used this fact. And so now we need to check this. No, we can check more general fact.
What you said?
No, in the proof of this theorem about that any module can be embedded to injective, we use some facts, and one of these facts was that if we consider, if we have these modules, we have left R module M over some ring R. If I consider Abelian group homomorphism from R to Q modulo Z, I have left R multiplication here, then on Hom I said before that I have right R module multiplication. And this is right R module. And I claim that this R module is injective R module. It's not obvious, but we use this in the proof. And now I want to check this. Okay, now we have something like this. We have ring homomorphisms. And for example, two parts. If I have some module, R module, left R module, and I consider tensor product, here I consider right R module structure on S by this definition. S multiplication by R is by definition S right multiplication by f of r. Then this is, and on this thing, I have left S module structure, no, by the by the multiplication on S from the left. Sorry. Yes. So this is left S module, and I claim that this left S module is projective if M is projective. So if I have projective left R module, it's R projective. Then this thing is S projective. For example.
S is what?
It's homomorphism of rings. I have homomorphism of rings. Then if I have left R module, then at first this tensor product is left S module by this definition. And no, I can construct this R module because I have right R module structure on S by this definition. On S, I have a right R structure and left S structure. It's SRB module, as I said before. I have two multiplication from S from the left and by R from the right by this definition, for example. And then I can construct this tensor product, and also I have left multiplication by S scalars. Okay.
So
This is left S module. Yes. And I claim that if this R module was projective, then this S module is also projective. And dual, if I have Hom over R from S to I is left R module. I consider left R module structure here, no, by definition, by the same definition, but from the left now. Then this, I can consider this abelian group, and in fact I have S multiplication on S from the right, and if I have S multiplication on the left side from the right, then on Hom I obtain the multiplication by S from the left. So this is also left S module, and I obtain, and I claim that if I is injective left R module, then this thing is injective left S module. It's dual part. And maybe you tell us why it's true. Or not.
I can do the first.
No, maybe you it'll better the second one because we used the second one. No, okay, tell us the first.
Because the first is obvious, at least for me.
Okay.
Because for the first you can use the fact that some
I hope you are not going to use the fact that projective are the direct sum of free modules.
yes.
No, then please, no, okay, then it's important, but then please prove this. Yes, it is, because it's another example that it's true that modules projective if and only if is the direct sum of some free module. And now your colleague prove this first.
Okay.
Ничего не видно. Так, я буду. Okay. I hope I don't. Okay.
So what's an easy part? This is easier. Okay. We need this.
Да не все равно.
So
For injective models, we don't have such easy criterion, but for projective, we have one.
I don't need this. I just need to. Then if this is free. So if this exists, if we have a map like this,
В другую сторону только. Должно быть из проективного. Ну, конечно, чтобы, ну, иначе сейчас у вас есть просто композиция, вам делать нечего, у вас уже есть композиция этих стрелок.
ну да.
I say that if you have arrow in the opposite direction, you already have a composition, you have no property. So you need to have this arrow. Because if you have arrow from down to up, then you have composition. And you know that there exists some u, and that such that p plus u is free. Yes, it's from the right to the left. Okay, yes. And then you need to construct the this.
Obviously, I have projection.
Okay.
Then the projectivity.
Because we know that free modules are projective. Yes.
Yes. We have like this. And then.
No, and also you have inclusion of your sum, and yes, and the composition of inclusion and this. Yes.
And I have I from the like this. Must be D or something there. Then we have H here, and
H is composition I and H tilde. H, как называется? По-английски tilde говорится. H tilde.
H is composition, yes. And we need to prove the commutativity.
Yes. No, that FH is G. Yes, it's something like this.
Yes.
We need FH G is equal to G. FH. Yes.
H, but this is by definition.
Yes, yes, yes. I. And we know that composition H tilde is the composition of
This is
G pi. G pi. Yes, G pi and I. G pi and I.
Give me.
No. It's you.
I cannot.
Yes. It's the end. It's the end.
This much idea. Okay.
Yes.
Yes.
It's G. Yes, it's G pi. Yes, it's this composition. This is G pi. No, the end. Okay. Cool. The opposite direction.
Yes. The opposite is like this.
It turns out that it's equivalent. Say that in fact, if we have any projective module, in fact, it's direct sum of some free module. Why?
We can.
Maybe you have ideas?
We consider like this. So the idea is that I forgot. Let me see. I need to.
No, we need to. No, I think we need to consider some particular case of this short cycle sequence and apply our general property of our module P.
You are right.
But what particular exact sequence M(n)(0) we need to
Yes. Okay.
consider?
Of course. If you take M equal to the free module, and this I'll take just an identity, and this I'll take this is for everything, and this is.
And we always have some surjection from free module. And then there exists H. It's kind of section of the surjection. Yes.
Since this diagram commutes, yes, we have like this.
No, and in fact, this already equivalent to say that pi is that H is the inclusion of direct sum. No, maybe you can prove this. Okay.
This is what I want to talk about. So from this I get that this is inclusion.
No, this is. Well, let me formulate this as a general fact. If we have some exact sequence, here is F, PP, surjection, and some kernel. Okay, it's always exists. And if we have section of this surjection, it's homomorphism such that this identity is this identity is this composition is identity. Okay. Then in fact, this section is inclusion is of direct summand, and this kernel is inclusion of direct summand, and f is direct summand of these two summands. Okay. No, in our situation, no, yes, and in our situation, f is direct summand of image of p and kernel of f. So maybe you now prove it, but this is general fact. Yes.
Yes. I wanted to say that obviously.
Also, if you have, in fact, if you have inverse on the left, that's also true. Yes, but now we have from the right.
I want to prove that this is the intersection Z.
So it's 0, huh?
This is question. So what does it mean? This means that if there exists an element, so okay, this is obvious.
No, yes, but if we have element from image of H and it's from kernel, then composition must be 0, but its identities cannot exist.
Yes.
Okay.
Why I don't need to continue. Is it obvious or not?
Now, yeah, this is maybe obvious, but maybe
Yes. So this means
but we don't know that this is exclusion. Maybe. Ah, no.
why this is identity.
Ah, yes, okay,
and,
yes, okay. You're right. Okay. And no, and the final part we need to check that sum is whole f maybe.
Yes. So this means that
That we have some direct sum. Yes.
This is indeed a direct sum, and this lies in f.
Uh-huh.
So we need to prove another conclusion. So I need to take some element x, and it goes like this. Okay, there is some trick. X minus I want it to lie in kernel of f, so this must be something h of
The objective is that here P is projected. So S tensor P.
No, now we prove this thing, and your colleague want to obtain this fact as a consequence of this fact.
So here we have proved that S is projected.
Yes, it's this is fact is kind of lemma for this fact. Yes. From perspective of your colleague.
Yeah, like this. So this is obviously in the image,
Yes, this is.
and this is from the kernel because.
No, because if you apply f, you obtain f minus fhf. Fh is identity. So, okay, yes.
This is identity.
Yes. So, okay. So we prove this fact, the criterion of projectivity. And now, your colleague want to use this criterion to use this criterion for this module. That this module apply this criterion if p is I'm sorry. Satisfy this criterion if p satisfies this criterion for R. Yes. Okay, of course.
With brutal truth, when I understand this part.
Okay.
Yes.
Me?
I don't want to be with
Okay,
that.
ask.
Okay.
Yeah, this part of the proof. How do we prove that? Well, if it's a sum of three modules, then it is projective. If you explain this, it would be.
Okay. We have this. You see that for we have some module P, and we know that for some module P exists another module such that their direct sum is free.
Yes.
So consider this. So okay, if we consider, I'll just.
Sorry, maybe we already know that free modules are free. Okay.
Do you
Yes.
agree that
Then it's a formal consequence.
so we need to prove that P is projective. We have some arrow G from B to N. We need to construct this arrow.
Yes.
Then we compute everything, must compute. Then everything is proved. So obviously we have a projection for first component, just piece of best projection, okay? So we have an arrow from here. But we have, we know that this is free, hence it is projective, then there must exist a map H tilde, because this is projective. But then we can include this in another direction. Inclusion goes like this. P goes to just the direct sum. P0. This inclusion. And this inclusion satisfies this property. This must be identity on what? E, P, on P, I think. Yes. Or
And the composition of this inclusion and H tilde, it's our
yes. But
map
then,
from P to M.
but then I can define the map like this, H. This map is from P to M.
No, right.
This is H. And this is, and we need to prove that this triangle is commutative, but this is true since from this manipulation.
Do you understand the second part? Because we also need the second part. We need criterion. Oh my god. In fact, any projective module is a direct sum of some free. No, in fact, here we prove that if we have, we don't use here that f is free. Okay? Yes, you agree? Do you agree that we don't use here that f is free in this argument? Okay?
Okay.
So in fact, we prove that if we have any projection from any module to projective module, then in fact it's projection on the direct summand. Then P that is the direct summand of M. And this is also equivalent to projectivity. It's another criterion, in fact.
But this is just fact about this.
No, yes, it's the same proof. We don't use here that this module is free. We prove that if we have some projection from M to projective module, then we have that this projection is a projection on the direct summand, and P itself is the direct summand of M. M is the direct summand of P and kernel of this surjection. No, and in particular, if we consider projection from free module, we obtain that P is always direct summand free module of or any other module which can project on it. Okay. No, and yes, and more or less obvious consequence, yes.
If we have a free module here, some free module, then this is just and this might be just
No, it also was some kind of exercise, but maybe it's kind of obvious, yes? No, that the product can use with direct sums, yes?
I think it was obvious.
Okay. So this is also an exercise that S standard R over R is S, okay, but it's also obvious. Okay. Yes.
I mean,
So this is free as module. So no, now we check that extension of scalars of free module is free module. Okay, it's kind of obvious.
And then,
because basis over R, if we consider it over S, it's basis over S.
Yes, but since now we have P is projective, then there exists U such that A for every alpha, such that E alpha is free. Yes, now I just want to construct a free module.
YP alpha, you have 1 pi, 1 p.
Okay, yes,
Yes.
of course, you're right.
P alpha was another exercise that the direct sum of some modules is projective if and only if each summand is projective.
Yes,
Maybe it's from
okay.
this, some memories.
I did this homework about 5 hours ago
Okay.
and had very bad sleep.
Oh my God. Okay, yes.
No problem.
Maybe you had dreams about this.
Okay, I'll just go in another direction. Just consider this. And this is times U.
No, it's at least sum of two modules,
Yes.
and this sum is free. So the direct sum is free, so your model is also the direct sum of some free model, yes. Because it's S tensor F, it's free. Okay, oh yes. Okay, okay.
This is obvious.
For example, opposite direction is not true, because if you have some extension over which you obtain projective model, of course, this does not mean that your original model was projective. Okay. Maybe you say us why the direct sum of modules is projective, if and only if each summit is projective.
Okay, just the same.
No, by this argument. Okay. No, of course, yes. No, but this is more or less obvious from the definition. Okay, I left this an exercise as it's an easy exercise. Okay, and the direct product of injective, if and only if each factor is injective. It's from definition. It's easy exercise on unwinding of definitions. Okay. Now let's check this thing by another argument, because we have no such easy criterion here. Another argument is adjunction. I thought that you will tell us about adjunction, because this is corollary of adjunction.
Yeah, I thought about adjunction.
Okay, adjunction is the following. What I mean when I say adjunction, I say something like no, in general or in particular case. No, let's consider in particular case. If I want to say something like this, Abelian. No, maybe yes, maybe S. What this thing? What? Okay. 1 second. Again, I have some ring homomorphism from R to S. Ring homomorphism. Change of rings. I have some R module. Left R module, for example. I can consider Hom over R from S to N. I consider S as right R module by this definition of multiplication by R from the left. And also S has right as a multiplication, and then this module is in fact left S module. It's left S module if you define what it's SF on some, I know, S prime by this rule. By this rule. You might check that if you write on the domain from the right on variables, you obtain the left module structure on functions. It was another exercise, but maybe if we will have time, maybe we will check it. But no, it's for you. Okay, it's for you itself. Okay, for yours. So this is left S module, and I can consider another left S module, something M. It's left S module also. And then I can consider its S module. This S module I can consider Hom as S modules from M to this Hom. Now I claim that this is isomorphic as Abelian group. It's just Abelian group if it's not commutative rings. It's isomorphic as Abelian groups to Hom from M to N over R. N is R module, and I can consider M as R module with the same rule. R M is F R M. M is S module, but I can consider it as R module through this homomorphism. Okay. Может быть, кто-нибудь из вас? Maybe some of you give me the isomorphism. No, okay, no, let's just give some candidates for these isomorphisms. If I have, no, for example, from left to the right, right to the left, no, from, I don't know, from left to the right, for example, I have some element from here. It's phi from M to Hom. Huh? Yes, M to Hom. So I have phi of M it's some element of S, it's some element of N. And I need to obtain some Hom from M to N. No, it's phi of M of unit of S. Okay. It's some, okay, it's homomorphism which sends M to the M of unit, phi M of unit. It's gone from M to N.
But why is 1?
What element you want?
You just take unitary element just for simplicity.
No, it's fact. No, you can consider another invertible element. No, but then you have another inverse homomorphism. No, one here. No, because general situation is when here is some bimodule, and then here it was tensor product with bimodule, and this with some element x tensor M, and this is of x. But here, identification S module M over R with M as S modules goes through this identification unit here. And this is why one here.
You want to define the inverse map, that's why you take unit.
Yes, I just don't want to discuss general bimodal formulation. It's what an exercises, but this is a particular case. This is we have this isomorphism by this map, okay, and from this map to another side. This is isomorphism of S modules, left S modules. Okay, this map you can check that this is map of R modules because of this map is a map of R modules. Okay, and another direction. If I have homomorphism from M to N of R modules, psi here from M to N as R modules, then I need to obtain phi, something from M to Hom. Okay, it goes to M, need to go to Hom from S to N, something like S to psi, S, something like this. It's from M, this from Hom from S to N. And again, you can check that this is R module map, and this is in fact S module map. So this is from this, and this is inverse map. And also you can check that this is this composition identities. These maps are invertible to each other, to inverse to each other. Inverse to each other. Okay. Okay. No, it's very explicit formulas. You can check all what I claimed. Okay. Okay, we have this isomorphism, and from this we can obtain the injectivity or projectivity. No, projectivity we have already proved. So let's obtain injectivity. I want to clear this part. Okay. I think this under it's on the video. Okay, so.
This Adjunction in particular, Adjunction, we used that our link is unital. I read somewhere that there is also some kind of Adjunction.
No, I said on the first lecture that all our rings will be associative and unital.
No,
yes.
I understand it, but my question is there also some injunction for this case? The ring is not unital.
No, there is general injunction if it's RSB module here, and then you don't need a unit here. If you have, but if your ring is not unital, I'm not sure. No, we need something like this. Yes. Why it's true? If R is not unital, I think it's not true just. Okay, and so we need some. We obtain some more complicated theory. I think this is true for unital rings. No, because no, you need, no, for example, map from here to here, it's some kind of multiplication. No, if R is not unital, you can consider R which acts by 0 on some module, and this is 0 map, so it's not isomorphic. If R is not unital, then module is not unital, and you can consider multiplication by zeros. By any element acts by 0. It's module map. It's module structure, but it's not isomorphic here. Okay. So we consider unital rings and such modules which unit acts by identity. It's unital modules. Unital modules over unital rings. Okay. Okay. Now, yes, we have. I consider Hom from S to I over R. I need to check that if I is R injective, then this thing is S injective. No, okay. I consider some injection of S modules. I have this map. I need to obtain this extension. This map is element from here. So this homomorphism is the same thing as homomorphism from M to I. So this diagram is equivalent to say that we have diagram of R modules and map to I as R module. But I know that I have extension here. And again, extension here is the map from N to I is the same thing as map from N to Hom. So I obtain extension here. Okay. No, by bijection. I have this diagram. This diagram is the same thing as this diagram because I have bijection between Homs. Because our maps, no, our arrows are in bijection here. But map from something to Hom from S to I to a coextended module is the same thing as R module map from map to I itself. Okay. And then I have extension here, and again this map is the same thing as this map, as S modules. R modules here, this is S module world, is R module world. No, I replace word category by the word world. Okay. Okay. And for projectivity, the same thing because we have another adjunction with tensor product here. In fact, we have Hom. If we consider something like R module S over R is S module, and if we have S module here, then as S modules is the same thing as Hom as R modules from M to N. And again, using projectivity of M here, we obtain the projectivity of this here by the same argument. And this isomorphism constructed at the same manner as this homomorphism. Okay. What?
This equation is signifying this diagram.
I don't understand what you mean.
This equation is signifying this diagram.
Я не понимаю, что он имеет в виду?
Он спрашивает вас, что какое-то уравнение как будто упрощает одну из диаграмм.
Я примерно так понял, это не очень понял. Я не понял. This equation means that these diagrams are equivalent. That maps from S module to module of this form, element from here, is the same thing as R module map from the same maps, from the same modules, considered as R modules, to I itself. No, I consider N is I here. And M here is M or N. They are M and N here are S modules. I can consider them as R modules by this rule. And if I consider them as R modules, then maps to I itself is the same thing as maps to this thing as S modules maps. This is from this isomorphism. And I have extension here, then I have extension here. But why this does not work? No, to say that this is equivalent to say that if I have injectivity here, then I have injectivity here because it's equivalent. But this is not true, and for projective it's not also true. What's wrong with this equivalence? It's not equivalent to say that if this module is S injective, then N is R injective. It's not true. because here, no, for injectivity I need any R modules. But here I obtain only such R modules which in fact S modules. And they are modules from this rule. Not any R modules comes from S modules of this form, okay? By this rule. It's not any R modules. It's injectivity only for such modules. It's true that if this module is injective, it's the same thing to say that R module itself is injective for inclusions of S modules, from R modules which comes from S modules. It's true. But it's not any R modules of this form. Not any R module has form that it's in fact S module, and we consider them as R modules by this rule. So it's not equivalent to say, but if our model is injective for any R modules, it's also injective for R modules of this form, of form as restriction of scalars from S modules. In fact, it's kind of restriction of scalars, yes. It's restriction of scalars. It's in fact, this is S modules, and I consider them as R modules by restriction of scalars. I don't write this, but it's подразумевается. What? Я даже не повторю. Ладно, окей. Okay. No, so we obtain that this is R modules, but in fact they are S modules. Not any R module, in fact S module. It's not true. You can consider R module which does not come from S module. Okay.
But this fact about this isomorphism that's from S and from R, like, is it true for any R tensor?
Of course. So if you have a homomorphism, yes.
Yes.
No, for unit. For unit associative. Not commutative, of course. So commutative we don't need here. If R and S commutative, then in fact this homomorphism is a homomorphism of R modules, because this is R module and this is also, if you consider R modules, it is in fact S module, but if you consider R module structure through the homomorphism, then this homomorphism is a homomorphism of R modules, okay. But in general, it's a homomorphism of abelian groups. Isomorphism, sorry. Okay. What about 5 lemma and long exit sequence of homology for short exit sequence of chain complexes? It's fundamental fact for homological algebra. We need to check them on the next seminar, on this seminar, or maybe you say me that this is obvious.
This is obvious.
This is obvious.
What? Can you repeat the fact?
If we have chain complexes, 3 chain complexes. Did you remember what the chain complex is? Chain complexes are some modules, and yes, it's chain maps of chain complexes such that for each I, it's short exit sequence of modules. It means that it's short exit sequence of chain complexes. Okay? Yes, and then we have homologies, and on homologies we have induced homomorphism, and in fact we have boundary homomorphism, and this long exit sequence. Long sequence of R modules is exact. Is it familiar? Will you check that by yourself and say me on exam without checking on seminar, okay? Or not?
Well, if you need to prove 6 inclusions, like kernel is an image and kernel.
Kind of, yes. No, it's very direct, yes. It's more or less. It's kind of diagram chasing, yes? No, maybe, do you remember the definition of boundary homomorphism, yes? Okay. No, and then, okay. And 5 lemma, yes? If you have 5 modules and 5 another modules, these arrows are exact in this place, And if you have comparing homomorphisms, then if these 4 homomorphisms are isomorphisms, then this middle homomorphism is also isomorphism. It's a 5 lemma, yes. Yes, it's also diagram chasing, yes. Okay. No, it's fundamental facts. I think we will use them. So, okay. Let me как бы тут удостовериться. О, я хочу сказать, что я хочу удостовериться, что вы это поняли.
to make sure that
Yes, you're right. I want to make sure that you understand these facts. Okay. That you, yes. Так, окей. Что-нибудь еще?
I did it once, I mean, like, in my life, I mean, like, this proof of the...
No,
sequence induces
maybe
exact-
it was to do this at least once at your life, yes.
Yeah, but it's kind
Maybe just before exam on homological algebra or something like this, but at once maybe it worth it. Okay, or maybe on exam if you get the ticket about this, huh?
I said if you dare.
Yes. Так, ну там еще были, it was exercises something about free but not projective but not free modules, yes, something like this. Maybe you can give me an example of module projective but not free.
So all three are projective, but not all.
Yes. For example, for abelian groups, you know that any subgroup of free abelian group is free. So for abelian groups, for modules over integers, for abelian groups is the same thing as modules over integers. It's the same thing. So for abelian groups, any projective abelian group is the direct sum of free abelian groups, so it's free. So for abelian groups, it's the same thing, projective and free modules. It's the same thing for any rings for which you know that submodule of free module is free. It's so-called principal ideal domains. For example, polynomials over one variable, it's also true. For polynomials of a field in one variable, it's also true that any projective is free. But in general, it's not true. No, there is very easy example. No, I said before that by Serre-Swan theorem, for example, if you consider ring of functions, then projective modules finally generated is the same as vector bundles, and free module is the same as trivial bundles. So, for example, if you consider two-dimensional sphere and consider tangent bundle and the corresponding module, then you obtain projective but not free module. But there are much more easier example. For example, if you consider ring Z modulo 6, maybe you give me example of two modules over this ring such that its direct sum is Z modulo 6, but none of them is free. No, yes, of course. You can easily define, no, if you have, what? Yes, if you have, я все время забываю, как будет, residue, да, which it. If you have residue modulo 2, you can multiply it by residue modulo 6 and obtain residue modulo 2, and also for modulo 3. So this is modules over Z modulo 6. And these modules, if you consider them together, it's isomorphic to Z modulo 6. So these modules are projective, but it's not free because no, they have less elements than Z modulo 6, so it's not free. It's not.
we can maybe then come to conclusion that we need to have Z over P where P is a prime number, right? Then
What?
everything is fine. Everything
No,
is
if
fine,
Z is prime, if Z modulo prime, it's field, and over field, any module is free.
yes, then yes.
And any module is projective and injective. Over fields, all vector spaces are injective and projective at the same time. Over Z, free groups are not injective. Injective are divisible groups. We proved this last time, yes. This is,
Can you repeat this once again? What's the point?
the point that, yes, these things are modules over this ring, and these modules are projective because their direct sum is free module, but they are not free in obvious way because this is not Z6 in some degree. And so this is example of two projective but not free modules over Z modulo 6. I think this is the most, no, maybe, no, yes, I think this is the most easy, yes, example, yes. The least semi-prime number, 6. Okay?
Are there any other, like, maybe less trivial examples of that?
No, less trivial examples is non-trivial bundles over spaces, for example. Or maybe, okay, ну нет, ну что-нибудь такое, нет, ладно. There was another example that, hello. There was another example that there exists a ring such that it's isomorphic to R plus R as R modules. So it's not commutative. We proved that for commutative ring, if your module is free, then you have a correct definition of rank, of dimension. But if R is not commutative, there exists some one-dimensional module which is at the same time is two-dimensional. Did you know the example? No, in fact, you can consider R Do you know the example? What? Scalar? What? Okay. No, for example, you can consider a ring of it's kind of infinite matrices. No, infinite. No, infinite. Yes, infinite matrices.
It means like they're infinite, but like the finite number of elements is not zero.
Yes. No, yes, something like this. So it must be the ring. So you need to to multiply to such matrices. Yes, and if you consider something like this, you can check that there is isomorphism of R modules. It's not isomorphism of rings. It's isomorphism of R modules. So over such not commutative ring, for example, you have no notion of dimension of free module of rank. But over commutative ring, you have this notion. Last time we proved that for any commutative ring, you have notion of dimension of free module, but for not commutative, not true. Okay, let's finish our seminar.